Have you ever wondered what makes some websites super fast while others make you want to throw your computer out the window? Or why your phone can search through thousands of contacts instantly? The secret sauce, my friends, is something called algorithms. And the way we measure how good those algorithms are is with a cool concept from computer science called Big O notation. It sounds intimidating, right? Like a secret code for super smart programmers. But I promise you, it's not as scary as it sounds. It's just a way of talking about how much time or memory a computer program needs to solve a problem. Think of it less like complex math and more like a rating system for your code. So, what does Big O actually do? Imagine you have two different recipes for baking a cake. One recipe tells you to add ingredients one by one, which is pretty straightforward. The other has you doing 10 different things at once. And it gets more complicated if you want to bake a bigger cake for more people. Now, one of the key ideas behind Big O is that we are often, let's be honest, a little pessimistic. When we analyze an algorithm, we usually want to know its worst-case scenario. Why? Because planning for the worst case means we're prepared for anything. Imagine you're looking for your friend, Alex, at a huge concert. Best case. Alex is the very first person you see. Awesome, but you can't count on that every time. Worst case, Alex is the last person you check. If your plan works even in that worst case, you have a solid plan. Computer scientists do the same with algorithms. They ask, what's the absolute maximum number of steps for input size n? That gives an upper bound, a guarantee. If our search is O(n), then for n items it will take at most about n steps. It might get lucky and finish in one step, but it won't take way more than n steps. Big O uses simplification rules. Rule 1. Care about the term that grows fastest. Example term, n squared. Example term, 3n. Example term, 10. As n gets huge, n squared becomes gigantic. It overshadows 3n and 10. The other terms are like a drop in the ocean. So we simplify and say O(n squared. We focus on the future bottleneck as data grows. Rule 2. Ignore constants. Example, 2n steps. Example, 100n steps. We call both O(n). Seems weird at first. Isn't 100n worse than 2n? Yes, in absolute terms. But both grow in a straight linear line as n increases. Their growth shape is the same. Both are much better than O(n squared, which curves up like a rocket. Big O is about the shape of the growth curve, not precise numbers. It's about classifying the forest, not counting every single tree. All right, let's meet the stars of the show. The most common Big O categories you'll encounter. First up is O(1), or constant time. This is the holy grail. An O(1) algorithm takes the same amount of time to complete, regardless of input size. A real-world analogy: grabbing the first book from a stack. In code, accessing an array item by index. Next, O log n, or logarithmic time. Super efficient and a little magical. As n doubles, runtime only increases by one step. Think of finding a word in a dictionary. You don't read every word. Instead, open to the middle. Decide which half to keep. Split in half repeatedly. This is called binary search. Fast for large, sorted datasets, like searching a contact on your phone. Then, O(n), linear time, intuitive and reliable. Double input, roughly double time. Now we're moving into the side of town where things can get slow. Really slow. Welcome to O of n squared, or quadratic time. An algorithm with this efficiency is one where the runtime is proportional to the square of the input size. If your input doubles from 10 to 20, the runtime doesn't just double, it quadruples. If it goes from 10 to 100, the runtime increases by a factor of 100. A simple analogy is trying to find if any two people in a room share the same birthday. You'd compare one person to everyone else, then the second to everyone else, and so on. You often see O of n squared performance when you have a loop inside of another loop, where both loops go through the same input. For example, checking a list for duplicates by comparing each item with every other item leads to roughly n times n, or n squared comparisons. fine at 10 items, about 100 operations, but at 10,000 items, it's 100 million operations. And if you thought O of n squared was bad, let me introduce you to its terrifying cousin, O of 2 to the n, or exponential time. This is where algorithms go from slow to, honestly, practically impossible. With exponential time, adding just one more item to the input doubles the runtime. This growth is explosive. Brute forcing the traveling salesman problem grows exponentially. Even 25 cities can be astronomical. Why this matters? Big O predicts performance as data grows. In interviews and real projects, that foresight saves time. On small tests, O of n and O of n squared can feel similar. At scale, differences explode. This is scalability in action. Compare solutions and pick the approach that scales better. Be ready to discuss trade-offs and complexity succinctly. Practical tip: sort first, or use a hash map.